So here's the basics of asymptotic analysis. Just remember, we're determining the time and space required to solve a problem with a given size of n. And n is the number of pieces of data that have been currently inserted into your algorithm. Again, this is a study of how the algorithm will behave as our n slowly increases. So does adding more n add a lot more complexity to your algorithm, meaning time as well? That's a problem. We're hoping that we're going to have a pretty much a flat line when we do a graph, and I'm going to show a graph here in a moment. But we're hoping that's going to be pretty predictable, and it's usually pretty flat if we just keep adding more and more data pieces into it. So first, in our big overall scheme of this is O of n. And that is the operational runtime of your overall function. N is the size of data input, and the input can be the number of bits, number of data pieces, some piece of data that's going in there. It has to be greater than 0 because otherwise we don't have a program if we don't have any data in it. And it can't be negative and half piece of data. We don't get into that crap. Again, we're worried about the runtime of the program. This is going to be a mathematical model. There's going to be some influences on it, like the CPU speed and stuff like that. We actually don't worry about that because we can predict that. We have well, actually, I shouldn't say predict, but we have some concrete evidence of what that's going to be depending on the platform that you're using. But we don't know when it comes to everything else with the size of the data. So that's what we're going to be worried about here in a moment. So here's an example graph that we would use for asymptotic analysis. So notice all the lines that are on this here. So f of n line that you see right and through in here is our real life, real world function or your coded application, how it literally performs if we were to set time and data to it in this graph. It describes our process and the running cost of our program. And we watch f of n growing as we're adding more and more data in it. So the further we go, the more and more data. The higher up means the more and more time that it takes. Now, the other line is our constant time, our g of n. This is our theoretical line. This line is another function or graph line that we're trying to mimic the same and very close to our f of n. So notice it's not perfect, but it's pretty darn close. Now the bad part is, and I'll get into this a little bit more, is that there's going to be some lines that are closer than other that mimic f of n a little bit closer. That's what we want. We want to mimic as close as we can to f of n as possible, and I'll explain again here why in a little bit. Our next item is our threshold or n naught. Again, I'm going to explain a little bit more of this, but at least wanted you to see it on the screen here or on a graph here. But that's actually where a certain spot where after there's a whole bunch of crap that's going on, which I'll explain here in a second, then we can start predicting from there on out at f of n what it's going to mimic and be in our application. So it's a really important line that I'll again cover here in a moment.